This project shows how the crocodile death roll shot in a lake was created with algae and underwater plants while addressing several technical simulation challenges. The first major issue occurred when enabling stick-on collision in the flip solver to add friction between the water and the crocodile's collision surface. While this helped create interaction, it also caused the water to remain permanently stuck to the surface, forming an unnatural shell around the crocodile. To resolve this, we generated custom velocities along the surface of the crocodile and injected these velocities into the flip solver. This allowed the water that was stuck on the surface to move along the body of the crocodile, producing more natural motion and significantly improving the realism of the interaction. The second issue appeared when running the simulation at very high voxel resolutions. At higher resolutions, the simulation began to lose velocity energy, causing the water to dampen much more than expected. Interestingly, this problem was not present at lower resolutions. The reason is that smaller voxel sizes produce a larger number of voxels, which increases the numerical error in the simulation. To overcome this, we generated velocity fields from a lower resolution simulation, extracted those velocities, and then injected them into the higher resolution simulation. This approach allowed us to maintain detailed motion while preserving the stronger and more natural velocity behavior from the low-resolution simulation. For the plant simulation, we used vellum cloth to represent the flexible plant surfaces. Different parts of each plant were connected using glue constraints, and to maintain the overall shape and structural integrity, we added an additional shape match constraint. This combination provided both flexibility and stability, allowing the plants to move naturally while still maintaining their form. For the algae simulation, we first created curves and applied noise to introduce natural variation. Points were then scattered along these curves and converted into vellum grains. Glue constraints were added between the points to create connectivity, which resulted in thin, strip-like structures that behaved like algae or floating plant strands. Finally, to ensure that the plants and algae floated naturally on the water surface, we used POP advect by volume. The surface field was used to drive buoyancy behavior, while the velocity field controlled the directional movement. This allowed the plants and algae to follow the motion of the water while remaining properly buoyant and dynamically interacting with the simulation.